All right, so we're continuing today in chapter 2, and we are looking now at the idea and the concept of energy. And so let's just start with some relatively simple definitions. So energy by definition, this is kind of your classic textbook definition of energy. By definition, energy is the capacity to do work. And so that capacity can be shown as either an observation of something actually doing work, like moving an object across the floor or throwing an object across the room, or that energy can be shown in the form of energy storage, where I know that there's a stored amount of energy inside of something, and it is just awaiting the opportunity to release that energy. Now, again, by definition, work is described as the force that is applied over a distance. And force can be measured as the product of the mass of a body and the force of gravity on that body. Now, don't get too caught up in the definitions in terms of the calculations, the equations. We're not going to use them. But we need to have an idea of where this all comes from. So, gravitational force, you have a force that's being exerted on you right now because you have a mass and gravity is working on you at this moment. That force happens to be what's sticking you to the floor instead of allowing you to float up toward the ceiling. Now, when it comes to energy, what we find is that there are basically two different forms of energy. There's the energy of motion. So when an object is moving, it is showing off its energy in the form of kinetic energy. And then there is potential energy. And that's, again, that's the idea of stored energy. Energy inside of something that is not currently being shown. But we know that it exists because when given the proper stimulus, that energy shows itself in a variety of different ways. And in the process, it converts from potential to kinetic, and in some cases, from kinetic to potential. Now, what does all of this, as any of this, have to do with chemistry? Well, in terms of chemistry, when chemical reactions occur, we're going to see this interplay between potential energy inside of the bonds that make up our chemicals and kinetic energy in terms of what happens when that chemical energy gets released. How does it get released? Does it get released as heat? Does it get released as light? When things get hotter, what happens to the molecules? Do they start moving faster? Do they potentially start to push against the walls of their container? Now, all of these forms of energy here kind of fit into that potential versus kinetic kind of idea. Radiant energy, thermal energy, sound energy, and even to some degree mechanical energy. These are all kinds of kinetic energies. Because these energies come out as a chemical reaction takes place and usually does something to the molecules that they interact with. Chemical energy and atomic energy, these we tend to think of more as potential energy forms. Chemical energy, we're talking about the energy that is stored inside of the bonds of a particular substance. And so long as a molecule keeps those bonds, that energy remains just that, it's stored. But as soon as we break those bonds and start to rearrange that energy can get released in the process. Same thing with atomic energy. This is where we get into that nuclear class that we'll eventually get to around midterm. Inside of the nucleus, there is a whole bunch of energy that holds that nucleus together. And most of the time, that nucleus is held together rather stably. But introduce the proper stimulus, say ejecting a high energy neutron toward that stable nucleus, and suddenly that nucleus isn't as stable anymore. And the energy that holds it together causes it to break apart. And when it breaks apart, that excess energy gets thrown out. And in a nuclear reaction, we use that energy, we harness that energy to convert it into something useful, electricity. In weapons of war, that energy gets used for mass destruction, which is why, for the most part, we try to avoid using those weapons. And only very rare circumstances have they ever come out. Now, all forms of matter possess chemical energy of some kind. And again, that chemical energy is stored inside of the particular makeup of the substance itself. What the ultimate purpose in this class is to help us to identify what those hazards are and how it relates to their chemistry. So if we can figure out what's going on inside of their chemistry, we can figure out why they're hazardous, and we can try to do things to negate their hazard, or at least treat their hazard when it comes up. So again, that's why it's important to know the chemistry behind the hazardous materials and not just memorize the placards. The placards are important. They tell us what's going on. That's really only half of the equation. We want to make sure that not only we know what they are doing, but in an emergency situation, how do we deal with it? Now, related to all of this is something called the conservation law. The conservation law applies both to mass and to energy. And so the law of conservation of mass tells us that in any process, mass cannot be created or destroyed. So it doesn't matter if we're talking about a chemical process like a chemical reaction, mass cannot be created or destroyed. Every single atom that we started the reaction with comes out at the end. Usually there's just a difference in how those atoms have chemically arranged themselves with each other. Bonds get broken over here, new bonds get formed over here. Energy is the same way. Energy obeys the law of conservation of energy. In any process, energy is conserved. So the total amount of energy that we started with is the same as the total amount of energy that we end with. The difference between the two is what forms of energy are being shown. So if our products are way hotter than our reactants were, it's not because they have more energy. It's because the form of energy that they exhibit is more kinetic than potential. Total energy is all the same. What kind of energy is being shown is what makes the difference here. And so we're going to pivot from energy to temperature. And the reason we're going to make this particular pivot is because temperature isn't a form of energy itself, but it is a way that we can get an idea of the amount of thermal energy inside of a substance. By measuring temperature, we can measure the internal energy, at least indirectly, of a group of substances. The hotter the substances are, the more internal energy they have. And generally that means the faster they're moving on the inside. The lower the temperature is, the colder they are, the less internal energy they have. Usually that means they're moving slower. So again, temperature isn't an energy unit, but rather an indirect measurement of the energy inside a system. We're actually measuring the hotness or the coldness of a system. And we can tie that energy, or excuse me, we can tie that temperature to an energy through the use of a couple of relatively simple equations. The two most common ways of measuring temperature are these: the Fahrenheit scale, which is the one that we are definitely the most familiar with. Fahrenheit scale is what is used for pretty much all of our temperature measurements here in the United States, unless you happen to be in a lab. And then there's the Celsius scale, which is pretty much used everywhere else in the world. It's also used by all of our scientists. There are a couple of important things to note about these two temperature scales. First of all, in both of these scales, we have values that have been defined systematically. So on the Fahrenheit scale, freezing was defined at 32, boiling at 212. On the Celsius scale, freezing was defined at 0, boiling at 100. Now, because of this definition, we can equate the two scales to each other. And the way that we set them equal to each other is based upon two things. First of all, there is a difference in the value. A 1 degree difference on the Celsius scale is not the same thing as a 1 degree difference on the Fahrenheit scale. If you look at the two differences, you can see that between freezing and boiling on the Celsius, it's 100 degrees. Between freezing and boiling, same two values, it's 180 degrees. So what this means is that every degree difference in Celsius is matched by a 1.8 degree difference in the Fahrenheit scale. You get that just by dividing 180 by 100. So Fahrenheit so just in the difference in their degrees, that's where the 1.8 comes from in our conversion between the two. But that's not the only difference. Yes, we have a different definition of what 1 degree means, but we also have what is called a scalar shift. Freezing on the one scale is 0, on the other scale is 32. So even if they were on the same 1 degree means 1 degree, there's still a shift of 32 degrees higher for the Fahrenheit scale. So for that reason, we've got to also add 32. Now, in some textbooks and some references, you'll see this slightly differently. You might see this as degrees Fahrenheit is equal to 9/5 Celsius plus 32. 9/5 and 1.8 are the same thing. The reason I favor the 1.8 is because when we have to go the other way, the multiplying by 5/9 sucks. And because of what we have to do algebraically, so the fraction 5/9 is not as clean. So again, to go from Celsius to, or from Fahrenheit to Celsius, you subtract 32 first, so you do the scalar shift first, then you divide by the degree difference. So those two equations are going to be really important for us because, again, to transfer from what we're most familiar with, Fahrenheit scale, to what we are more going to be more inclined to use in laboratory, Celsius scale, we have to be able to go between the two temperature areas. And there's one other reason. We've got to introduce something called the Kelvin scale. Kelvin scale is unique for a couple of reasons. First of all, unlike the Celsius scale and the Fahrenheit scale, which were defined based upon the freezing point and boiling point of water. So unlike those, there's only one point of emphasis on the Kelvin scale, and that is the 0 point on that scale. Kelvin can be directly associated with energy. I mean it in the most simple way of saying that. When there is no temperature, there is no molecular motion, which means that there is no kinetic energy. We call that absolute 0. That is the only point that is defined on the Kelvin scale, the 0 point, absolute 0. Everything else is an absolute measurement of the energy. So if I have an object that is at 100 degrees Kelvin, and I double the temperature to 200 degrees Kelvin, the energy of the molecules that were at 100 degrees are now twice as much energy at 200 degrees. If I go from 200 to 400, the energy inside will double again. And from 400 to 800, the energy inside will double again. We can't say that about the Celsius scale or about the Fahrenheit scale. Today it is supposed to be 40 degrees. Tomorrow it's going to be 20. Is it literally going to be half as warm tomorrow? It's going to feel pretty much the same. The only difference will be you want to wear a hat and a scarf or just a hat. So that is an important difference. And the reason we use the Kelvin scale, and we're going to get to some applications of the Kelvin scale at the end of this chapter. But the reasoning behind it has everything to do with that energy. And we want to be able to mark energy appropriately. And that's what the Kelvin scale is for. Now, there is another version of an absolute scale called the Rankine scale. We're going to avoid it. Mainly because the Rankine scale matches up to the Fahrenheit scale. And for us, it really has no utility. We're going to focus on the Kelvin scale because the Kelvin scale matches the Celsius scale in one very, very important area. Again, notice what we did on the previous slide. 180-degree difference between boiling point and freezing. 100-degree difference on the Celsius scale. 100-degree difference on the Kelvin scale. So what does that really mean for us? Well, it means that Kelvin and Celsius are on the same scale. A 1-degree difference in Celsius is a 1-degree difference in Kelvin. The only thing that we have to account for is the shift. And the shift is 273.15 degrees. So to find Kelvin, I take Celsius and I add 273.15 degrees. That's all I need to do. No multiplying, no dividing, because they're on the same scale. Right. Any questions about temperature? Nope. No, there will be no questions about it. Like I said, I know it's there. I know it has a very limited window of industrial uses, but again, those would be very localized. And honestly, most people just will use the Celsius and Kelvin scales, especially because if you look at the scalar difference there, it's not a very clean number. It's 459.67. The Kelvin scale has been around for considerably longer. Yes. No. We So theoretically, we know it exists. In experimental practice, we have not been able to observe absolute zero. And the primary reason for that is we cannot create it artificially. Because any means that we can, we've gotten close. We've gotten within a couple of tenths of a degree of absolute zero. But the amount of energy withdrawal that would have to take place to get it down that low, we just can't achieve. Because regardless of whatever means we are using to pull the heat out, some heat is going to go back in. Even if it's tenths or thousandths of degrees, it's still going to go back into the system. So we know it exists. No, because we know that there is molecular motion in space. So while space is definitely cold, at least in the areas that are far away from stars, we also know that there's molecular motion in all of those objects. I mean, track a comet hurtling through space. You're going to find that, yes, it's cold, certainly uninhabitable, but is it going to be so cold that nothing is moving and only acting on gravitational force? No. All right, let's pivot to pressure. Now, pressure is also related to force. So we talked about energy. Energy was force applied over a distance. Pressure is force applied over an area. So now we're talking about a two-dimensional force as opposed to a one-dimensional force. Now, there are lots of different pressure units. The one that we're most familiar with is the PSI, the pounds per square inch. Pound is the unit of force. Square inch is the unit of area. But again, that's a familiar system. That's the customary system. The SI system, on the other hand, uses something called the Newton. The Newton is a kilogram that is accelerated at a rate of 1 meter per second every second. Where pressure is most important to us is with gases. And the subject of pretty much the next 2 days of lecture is all about gases. So where we use pressure most often is in the measurement of gauge pressure. So how much gas is left in this particular tank or in this particular gas cylinder, or how much gas is left in your car tire. And the reason we use it in this way is because we can relate pressure and amount of gas to each other. So by measuring the pressure, we also measure the amount. And so you're probably familiar with this. This is just kind of a typical pressure gauge. The numbers here all vary. So the red numbers here represent PSI. The blue numbers here represent something called kilopascals or bars, which are the metric unit. What kinds of pressures are we ultimately concerned about? Well, the first one is atmospheric pressure. Atmospheric pressure is the pressure that is exerted on you and on all objects by the gases that exist in our atmosphere. So this is a relatively constant amount of pressure that is going to be felt by every object on planet Earth. Now, how much pressure are we talking about here? Not much. At sea level, which is pretty close to where we are, we're only a couple of 100 feet above, it's about 14.7. If we are using a barometer is basically kind of like a large thermometer. It's filled with mercury and it's open to the atmosphere. The higher the mercury climbs, the higher the pressure is. That same sea level air will push mercury up a column 760 millimeters. So that's 0.76 meters, which is about 29, almost 30 inches. So by definition, one atmosphere, atmospheric pressure is equal to that 760 millimeters of mercury and also that 14.7 psi. And there are other pressure units as well that we'll get into here in just a minute. Now, an important note, kind of calling back to where we were last week, notice that all those are equivalent to each other. And so for that reason, we can pick out any two and convert from one to the other using that factor unit method that we talked about last week. Mercury. So mercury Hg, that is what goes inside of a barometer. And basically you put a ruler up to it and you measure how high up it goes. So barometers are in some ways very similar to thermometers, in that a thermometer works by the heat energy that you exhibit causes the liquid inside to expand and go up. A barometer works by the pressure of the atmosphere pushing down on the mercury and forcing it to go up in the tube. The more the atmosphere pushes, the more the mercury goes up. The less the atmosphere pushes, the less it goes up. Now, in our lab, we do have a barometer in one of our instrument rooms. And so, it's one of those things, if you asked Mrs. Eagleson to just show it to you real quick, she would. But the idea is there. And again, it's an instrument on the wall. And right next to it, we've got a meter stick taped up so that you can count the millimeters. Some other forms of pressure. So atmospheric pressure was the pressure of the atmosphere on a substance. Vapor pressure is the pressure exerted by evaporated liquid. So when we say vapor, that's what we mean. We mean we had a liquid and that liquid has evaporated. And the vapor pressure is how much pressure, how much force is being exerted by that evaporated liquid on its surroundings. Now, every liquid does some evaporation and has some vapor pressure associated with it. Even the ones that we don't consider to be especially volatile. So water, for example, and you guys know this. You've seen it in action. You just didn't know what it was when you saw it. Ever leave a glass out on the table all day? You notice that the water inside dips a little bit when you do. That's evaporation. Now, the reason why the water level went down is because moving air inside of the room pushed out the evaporated liquid and allowed more to evaporate. If you had put a lid on top of your cup, that vapor would have been trapped and it would have exerted a pressure. It wouldn't have exerted much pressure. If atmospheric pressure is 760, room temperature water exerts a pressure of about 21. So not terribly much in the scale of things. Talking what, 3-4% compared to the atmosphere? But still enough that you would notice it was gone if you let it just continue to sit there and sit there and sit there. Vapor pressure is often measured in millimeters of mercury because the values do tend to be lower, or kilopascals, but that again, that's a little bit more rare just because of how small vapor pressures usually are. If we are looking at liquids that are considered volatile, volatile just means that it will evaporate easily. Important note here at the bottom. Just because something is volatile does not mean that it is flammable. Volatility and flammability are two different properties. Now, that being said, if something is flammable, it usually is volatile as well. But the reverse is not necessarily true. And so when we describe a volatile liquid, what we're describing is a liquid that at room temperature will pretty easily evaporate. And most of the ones that you can think of also are flammable as well. But again, it's important to note, just because it is volatile does not mean that it is flammable. All right, so the last thing that we're going to talk about today is heat. Now, we've already kind of nibbled around the edges of heat. We talked in particular about temperature and how temperature is a measurement of the internal energy of substances. Heat is a form of energy that is also associated with the motion of molecules and atoms. We actually can use temperature readings to tell us which direction heat is going to flow. Because heat always goes from an area of high temperature to an area of low temperature. Now, we see heat come up when any one of the following things happens. So if we see a change in temperature for something, that is a result of heat. Heat's flowing into the system and causing it to go up in temperature, or heat is flowing out of the system and it's dropping in temperature. We see heat come out when physical changes occur. Ice melts into liquid water. Well, the primary reason for that, heat went into the ice, caused the ice to redistribute the way that it was interacting with each other, and it went from the solid phase to the liquid phase. We can also see heat changes happen when we have a change in chemical identity. And again, heat flow always happens in this direction. You go from an area of high heat temperature to an area of low temperature. The hot object always warms up the cool object. It doesn't go the other way around. All right, last slide for today. We have names for the processes involving heat. When a substance absorbs heat, takes in heat, and as a result, its temperature usually goes up. That is called an endothermic process. In an exothermic process, we see the temperature of the substance go down and the temperature of the surroundings go up. That's because heat is being released to the surroundings from that system. And again, heat is always going from warm objects to cold objects. Now, one thing to be careful of, especially here, when it comes to chemical reactions, exothermic processes will often feel warm to us because we're not part of the reaction system. We're part of the surroundings. And so, for example, when something catches on fire, we know that fires release tons of heat energy. And we feel that heat because we are on the outside looking in. On a chemical basis, though, those chemical bonds that are being made release all of that heat. Their internal temperature, their internal energy goes down. We feel the results of that. So it's very easy to get confused. Make sure that you're taking into consideration your standing. Where are you? Are you part of the system or are you part of the surroundings? If you're part of the surroundings, it's going to feel like the opposite effect to you. All right, that's where we're going to close it for today. On Wednesday, we'll pick this up and we'll start talking about gases. Have a great day.